A very good morning to you all. Welcome to a 5-day GYAN course on non-invasive diagnosis of propulsion motors used in electric vehicles. So this is the last day of this GYAN course, 5th day. So we had good experiences all these days, and yesterday in the morning session we had a session on switch reluctance motor drive systems, like modeling, simulation, control schemes, as well as fault tolerant motor drive systems also for the SRM has been discussed. So in the afternoon session you had a discussion on opportunities and challenges of using artificial intelligence for condition monitoring of propulsion motors has been discussed. Also in that session some activity based on these non-invasive fault diagnosis using data driven approaches also has been done by the Professor Ilampati sir. So it was a nice experience for the participants as well. So today, the 5th day, in this session you will be having the session on comparative analysis of conventional neural network based fault diagnosis with artificial neural network based fault diagnosis. So after that further the session will be continued, and we will have a valedictory function and also examination. So first we will start the session on comparative analysis of convolutional neural network based fault diagnosis with artificial neural network based fault diagnosis. Over to you, sir. Thank you.
Good morning, everyone. I hope you had a nice evening, and we have come to the final day of the workshop. So in this session, if my understanding is right, we will have a slightly different break time. So the intervals will be slightly different. And I'm planning to give some time towards the end of this session for us to debrief, discuss and ask questions about the overall course, overall workshop itself. So we will plan for approximately 2-hour session with a small recess break in between, and then we will have 30 minutes to discuss if there are any questions. Even some of your questions that I could not answer earlier, probably I will try to answer them now. Okay, so that is the idea. So the session itself may not look long, because we are going to introduce, learn about a very special machine learning method, or actually it's kind of a deep learning scheme. So how many of you here are familiar with CNN, convolutional neural network? A couple of you. Okay, three people. Okay, that's fairly big number. So we will. So once again, my intention is initially to introduce you to some of the key terminologies, so that you are not unfamiliar when you start reading about CNN in future. Okay, as I said, you cannot become an expert in these methods by listening to a person speak for just 1 hour or 2 hours, right? You have to read, practice, so it will take some time. But my intention is to help you acquaint with certain key terminologies, so that when you go through these articles, you have a certain degree of comfort. So the main intention is to actually compare the performance of a CNN-based fault diagnostic scheme with an ANN-based fault diagnostic scheme. And in order to do that, again, I am not going to go into the depth of implementing CNN, because with my goal of fault diagnosis, I am utilizing tools like MATLAB to implement CNN. But you will understand that the mathematics of CNN is not too different from the mathematics of ANN to some extent, and then there is also additional components. So we are not going to go in depth into the mathematical part, but you will see how they are different. Okay, so for some reason I always get my animation wrong on the opening slide. So I will start with a basic introduction to convolutional neural network, like a background, and then a little bit of definitions or ideas after the background. You will see what is a 1D CNN. It's usually a one-dimensional CNN, and why is it called a one-dimensional CNN, and why are we even looking at that specific CNN in this workshop, okay? And that is the main focus of this session. So you will realize that the CNN itself is something that generally is used for a particular application, but we are going to narrow our focus on a specific topic called 1D CNN, and it will address some of the issues we faced yesterday or identified yesterday. Then we will go through the key terminologies, and then finally, using a research article, you will be given time to go through the CNN part and then check the results with ANN, and then we will discuss and debrief. So it's a more an activity based last bullet is like that. Okay. So introduction to CNN. Okay. So I have to ask you a question before we even get started. Maybe I should have added a photo of person, then it would have been easier. But anyways, this is not a bad thing. If my pen cooperates, then we should get going here. Yeah, perfect. So you have to identify what I have on screen. Can you identify what I have on screen? What is the first one on screen? 8. What is the next one on screen? What is the next one on screen? What is this one on screen? 8. So our vision is capable of identifying images irrespective of how the features are changed. Okay? For example, no matter whether I have a beard or whether I lose my hair, you will still recognize me, hopefully, right? So the human vision has that ability. And just like how ANN is inspired out of biological neuron, the concept of CNN is inspired out of biological vision. We are trying to come up with a machine model that can, in a sense, not be confused by the different aids that I drew on the slide. Okay? So it is able to identify a person irrespective of the change of colored shirt, or whether the facial, like whether I had a haircut or not. Okay? So all those things is what CNN's inspiration. So basically CNN is inspired from biological vision. Okay? So this is the first thing you need to be aware. How our brain processes. So it will be very similar to ANN. There will be some inputs, activation function will be there, and then an output will be arrived at. Okay? So that's a very similar structure. So there is ultimately there are nerve cells, neurons, right? So you will see that the ANN architecture will somewhat be preserved even in CNN right away, the moment we put it this way. So why CNN was even developed? CNN was developed with a goal, with a primary intention to classify images. Okay? So all your CAPTCHA originally has intention, right? So you are able to identify what is a cat, what is a street light, what is a cycle, like that. So classifying images was the primary intention of CNN. So images, when we say images, images can be two types. One is a grayscale image. Okay? Grayscale image is black and white. So usually a CNN, if I consider CNN as a black box, so this is my CNN, I don't know what it is, it's a black box. What we will be doing is we will be feeding in an image into the CNN. And we will be training this to classify it, whether it's a cat or a dog or whatever that is. Okay? So we will have to know the ground truth. We will feed in multiple images. We will say this is cat, this is cat, this is cat, no matter how the orientation is, how the color is, okay? Whether the face is turned, whether it's facing the camera, all those changes, we will train the CNN, convolutional neural network, and ultimately we will get out. But what I want you to be aware is when we are talking about grayscale image, we can divide this into pixels, right? So any image can have multiple pixels. So each square is considered as a pixel, let's say. So pixel will be a value between, if it's an 8-bit pixel, you will have a value between 0 to 255, depending upon the image intensity, whether it's too dark or too light, what is there, right, in a grayscale image. So each of these is a pixel and it's a value, right? So clearly a grayscale image has values along x-axis, values along y-axis, right? And this entire image is fed into my CNN. The values of this entire image is fed into my CNN. So what is the nature of the input? Is it a vector or a matrix? It's a matrix, right? So the first thing I want you to understand is in ANN, whatever I presented to you, we had a feature vector that we presented. But CNN, when it is originally developed for image classification, it is capable of taking matrix. And any grayscale image will be a 2D matrix. It will have an x-axis and a x-axis and a y-axis quantity, right? The pixel location. So the grayscale CNN will be called as a 2D CNN. Two-dimensional input is being fed into my CNN for training and model development. Okay, grayscale is very boring. We all have colored shirts. We want our colors to appear in images. So what happens when we have colored image? So when I have a colored image, when I have my colored image, so digitally a colored image is a combination of 3 channels. One is a red channel image, one is a green channel image, one is a blue channel image, right? So basically this is the same size. I have just drawn it as a smaller box. So we have 3 channel inputs. Each one will have pixels. Right? So each one is a 2D matrix. But there are 3 such 2D matrices. So when I feed in a colored image into my black box called CNN for training purposes, what is the nature of the input? It is actually a x cross y cross number of channels, which if I call n or z, it's a 3-dimensional matrix. So it's a volume input. Not just length and breadth, but there is also a depth. Okay? So you can actually give image which has 3D. So you can visualize, like capture 3-dimensional things and put it in, like in 3 dimensions is what is the input we are saying. So this is a 3D CNN. Okay? So depending upon the dimensions of the input, we call the CNN as 2D or 3D. And primarily, when CNN was developed, the primary purpose of CNN was to do image classification. So we always started with grayscale and then colored image. So these were the 2 primary things. Now interestingly, for our topic, which is non-invasive fault diagnosis of propulsion motors used in electric vehicles, why are we bothered about CNN? Are we going to take pictures and feed it in? Is that the intention? That is not our intention. So yesterday when you were discussing about brainstorming about the challenges, one of the key challenges that we found when we wanted to use artificial intelligence method like ANN was feature selection. So if you recollect the article that I shared with you, I have selected time domain features of my stator current such as RMS, mean, skewness, kurtosis, like that. There are also frequency domain features. Okay, so the frequency, magnitude, bandwidth, so many things can be, in the frequency domain, the waveforms, different frequencies can be identified and their magnitudes can be used, right? Now, what we are unsure is which features to select, how do they impact, okay? We can of course do a principal component analysis and we can see if there are any uncorrelated features, then we can use them. If there are correlated features, then we can remove one of them or reduce the dimensionality. But we are still unsure how these features impact the result, right? So in order to mitigate the variation in the results caused due to feature selection that we will be doing, what we wanted to come up with as a solution is, why don't we use the machine learning model to automatically select its features? Okay, so the goal is feature selection to be done by my model itself. In other words, I don't want to extract features from raw data. I will do raw data, I will collect, I will do some processing like removing noise, normalizing, scaling, all those things, but I won't extract features from my raw data. I will have to feed my raw data into a black box model, which should have the capability to extract features. And then once the features have been extracted by it, it will use it for, basically an ANN will be at the back end, and that will do whatever we learned the other day. So once features have been extracted, that feature vector would be fed into an ANN model, fully connected ANN network with multiple hidden layers or one layer with many neurons, and it will do classification. It could be a binary classification or a multi-class classification. Okay. So this is the goal. Our goal is to, in fault diagnosis, in this case, the reason why we are even looking at CNN is we are trying to eliminate the necessity for us to feed in the features explicitly. Okay. So now let us look at the data that we have. The data we have is a current waveform, right? Line current waveform. So how will it be? It will be magnitude versus time. So in that sense, since it's just a time series, we can only use the amplitudes of the current and we can feed it into our CNN. So when we do that, when we have a black box CNN, and when I have just a time series input, so time series, okay, so it's like audio signal, current waveform, so the vibration signal, all those signals that we acquired from sensors are time dependent signals, like there is only one dimension and it's a function of time. So we will not input the, like we will remove the time information and we will just use the amplitude, and this now becomes just a one-dimensional input. So we now have a 1D CNN. Okay. So if you, at the end of this workshop, if you go outside and tell that you have learnt about CNN, you are actually misleading people, right? Because CNN by definition is something used for image classification where the input is 2D, 3D like that. But our focus is completely different. We are just wanting to be lazy, just avoid feature input as a feature cell, giving inputs of features to the model. Therefore, we want to use the raw data after some basic processing, of course, like noise elimination, noise cancelling and other things. So we are just using just a processed data from a sensor. It can be vibrational sensor, acoustic sensor, current sensor, voltage sensor, or it can be combination of all sensors concatenated into a vector. Okay, or put in vector form. So it is a single dimensional input, and that is why we call this as a 1D CNN. Okay, and this is what we will learn in this session. Some of the interesting aspects is the terminologies. Actually, because of the history of this model development, 1D CNN was not developed first. So in some sense, scientists learned to run first before they could walk. So they started with 2D, 3D, and then they also realized they could bring down the dimension to 1D and use it for audio signals for some other applications, right? So the terminologies that you will see associate with 1D CNN are exactly the same terminologies, except that the dimensions would be on the higher side. So terminologies will still be similar, which helps you if you want to not focus only on fault classification, but if you want to apply CNN, let's say you want to do thermal imaging of your power electronic converter and feed it into a CNN, you can still do it, and you can still learn. The terminologies will still help you get started. Okay, so that is the idea. Okay, so all this while we have been talking about convolutional neural network, abbreviated as CNN. So what exactly is convolution? We all would have learnt it in engineering, but so to quickly recollect, convolution is if there is a function f, which is a function of time, if there is another function g, which is also a function of time, convolving these two functions means you take the value of f at a particular instant, let's say tau, do a multiplication with the flipped value of this function g. So you do a minus tau and you do a shift. And every instant from minus infinity to plus infinity, you will be doing this mathematical manipulation. This may be very mathematical or abstract. So if you want to do a simple pictorial representation, let's say this is a function f, this is a function g. First you need to flip it. Flipping g means it will look like this. Then for every instant, so you will basically, if this is flipped g, then the first instant you will move this g somewhere here. And then you will try to do a multiplication and you will evaluate, you will get an output. Then you will move the g further, one sample or one time, like next tau. So the function would be like this, right? So you will see at every instant you will get a different output. Okay, so multiplying function f with a shifted, the flipped shifted function g would get you the convolving mathematical function. So this is a convolution in time domain. Typically, interestingly, when you do convolution in time domain, if you look at it in frequency domain, this is equivalent to, in frequency domain, just multiplying the signals in frequency domains. So it should be, if you do a frequency transformation, so time function is converted into frequency domain, g is also converted into a frequency domain, you just multiply the two signals in frequency domain, that is equivalent to convolution. Okay. Okay. So in case of, for us, if you really look at our data set, like a raw data set, which is acquired by a sensor, our sensor, even though is sensing a continuous time signal, like a current or a voltage, which is continuously there, which is an analog signal. So if I plot my current, it will be like this, right? So this is my current with respect to time, ampere in, say, seconds. It's a continuous function, it's an analog function. However, when I use a sensor to acquire it, I'm actually sampling it. So I'm doing an analog to digital conversion, and I'm doing a sampled storage of data. So my data itself will not be like this, but instead, depending upon the sampling rate, if I have 60 samples per second or 50 samples, 60 samples per wave or 50 samples per wave, I will have so many points. So I will start with 0, then here, then here, then here, then here, then here. like this, right? So this will be the samples that I will be working with. So each one is a sample, and this is the sample that will be stored in my data set. So my data set is actually sampled data set, right? All your data acquisition is converting analog to digital at a sampling rate which is high enough that you can preserve the nature of the wave shape with all the frequencies of interest. So what I want you to be aware is this mathematical equation is useful from continuous time signal perspective, but for all practical purposes we have to deal with the discrete time signal, because that is what we will get as a data set. And in discrete domain, what is integration in discrete domain? It's a summation, right? So what you will end up getting is your convolution would be a summation of sampled f times a shifted sampled g. So the product of I do not know how we will represent it in so it will be a function of sample, and then I do not know, it will be k minus n or something like that. So it will be a shifted sample, okay, flipped shifted sample. Maybe my notations are not right, but all I am trying to say is we are going to do sample by sample multiplication. So it is, in some sense, it is, if I have a function and if I have one value and another value, I am multiplying them and adding the whole sample length. So it's a sliding dot product. So what I am trying to say is we call this as, in discrete domain, we call this as a sliding dot product. Okay, so we will go one sample, multiply, add, like that. So this is the foundation of 1D CNN, why we are even looking at it and what it is. Ultimately, we will be doing multiplication, addition as mathematical operations on two functions. One of them is actually the original data set. Another function is something we have to identify. Okay, so this data set is usually the function f in C. Okay, what it will be convolved with, we have to define. Okay, and that is usually defined as a filter. Okay, and the general convention is to have a filter whose size is typically much lower than the size of the data set. Okay, so we will get into that in a moment. Okay, so until now we know we have a black box called CNN. So this is my CNN, and what is the goal? My goal is, if I give raw data set in one dimension, if I just feed that in, it should do feature extraction, right? And then after features are extracted, what should happen? It is basically an implementation of ANN, a fully connected ANN. So what you will realize is, in all CNN, the back end is something, is a fully connected ANN. So there are two distinct parts. The first part extracts features, and the second part is just our traditional ANN, where you will have the feature vector feeding in, and then there are, this is the input layer. So whatever comes out is going to be the input layer. Then you will have hidden layers with multiple neurons in each hidden layer, and then you will have an output layer. The output layer's output will be y hat, the prediction. And we will know the ground truth whenever we are training. We will know the ground truth y. So y minus y hat absolute value will be used for training. That will be the loss function, and our objective is to minimize the loss function. And how will we do? We will have to minimize the weights, but it is not only the weights of ANN, but also the weights that is helping us to extract the features. Okay, so what I am going to do now is I am going to show you. So this part I hope is already known to you. So my assumption is you know this architecture. So I am not going to draw this again. So it will have multiple hidden layers, fully connected. So usually this is also called as a dense layer in CNN. Typically it's also called as a dense layer. So what exactly is happening here in feature extraction part? In feature extraction part, we have what is known as a convolutional layer. So what does a convolutional layer do? It basically implements the mathematical convolution operation on the raw data set. Convolution operation means you have to take this signal, multiply and shift with another signal essentially and add, right? So we will check that. What I will explain to that. I explain that in a minute. Once the convolutional layer is completed, then usually there is another layer which is called as pooling layer. So there is a convolutional layer, there is a pooling layer. The output of the pooling layer will typically go through what we call as a flattening layer. Okay? We will talk about flattening layer and all these things in a moment. So there will be another layer called as flattening layer. You will see why it is needed in a moment. And then the output of flattening layer is basically the feature vector that is being fed into the back end, which is the dense layer, which is fully connected ANN. Okay? Okay, so just I hope this architecture is clear, right? So basically we have a big black box. The output half is known to us already as an ANN architecture. The input side of that black box is what we are doing as a convolutional operation. And then there is another operation called as a pooling operation. And then we will have to do flattening, and you will see why they are needed. Okay? But ideally, because this is the operation that dominates in feature extraction, this actually results in extracting features. This is the one that extracts features. So that is why this method is called as a convolutional neural network, because it is able to extract features. Then there is a neural network to do that. Okay, so the basic, the key terminologies I wanted to say are these: convolutional layer, I have already mentioned that, pooling layer, and then flattening layer, and then you have your fully connected ANN with its own hidden layers. It can be multiple hidden layers or one hidden layer and output layer, and the output layer's output will be the y hat, predicted output. Okay. So now let us dive into how this actually might work. So let us look at what is 1D CNN. So let us consider a sampled data set. Let us say I will give you some numbers: 2, 1, 0, -1, -2, -1, 0, something like that. This is my sampled data set. This is in convolutional operation. This is our function f, which has to be convolved with something. So please note that in our application we are using raw data, right? Because that is our goal, to use 1D CNN. But in general, in CNN algorithm, you can feed features here. It is not always necessary that you will only give raw data set. In fact, in CNN, when you do 2D, 3D, you can also input features as the input. Okay, so in our application, since we do not want to be bothered for feature extraction, we are using raw data set. Okay, but in many applications, you can actually extract features and feed them here. Okay. So this is either called as the input or also called as the feature vector. Now in order to convolve this, we need another function, and that is usually a size lower than the input vector. Let us say I will use just one sample, and this is called as filter, also called as kernel. If you go for higher order or higher dimension, typically called as kernel, but in 1D we can call it as a filter. If you actually recollect digital signal processing, you will understand why this is a filter, because when you do this kind of operation, you will be filtering out, right? So what we can say is, let us say this is 5. When I do the convolutional operation on the input data set with a filter of size 1, whose weight, so this value of 5 is the weight of the filter. So this 5 is the weight of the filter. The size is how many squares I have here in this diagram. So it's a size 1 filter. Okay. So when I convolve this, what will I get? I will get this. So basically 10, then I will move this. So first I will align my filter with the first sample, I will convolve, then I will have to shift. Can I shift here? Can I shift here? Can I shift here? All are possible. So by how many samples I shift, that movement is called as a stride. A stride. So when you walk, how far your next step is, that's a stride, right? So you can take a stride of 1, a stride of 2, or stride of 3, and so on and so forth. So your filter can actually take strides of different lengths. So the stride, usually we will say stride 1. So if it is stride 1, once this convolution operation is done here, this 5 will be moved to the next position. So this is what I want you to understand very clearly. So first filter was with sample 1, it did a multiplication operation, then because of stride is equal to 1, filter moved to next sample, shifted by 1 sample, then it will multiply, 1 into 5 is 5, then because of stride 1, the filter will move, 0 into 5 is 0, then again stride 1, minus 1 into 5 is minus 5, like so on and so forth. So what you will realize is, because your filter is nothing but a number, in this case with filter size 1, all it does is just scale your input, right? It does not do anything else. However, you can have a filter size greater than 1. Okay, so let us look at that convolution operation as well, and then you will appreciate what is really happening. So is this clear? So this is the first simplest case, which is probably not at all useful. We will never use such a filter size, but at least you get some basic terminologies out of it. So what you get out of this at the end of this exercise is an important terminology. It's called as feature map. Very, very important name. So you start with feature vector, you convolve it with a filter, what you get out is a feature map. Okay. So for those of you that are familiar with CNN, this might be very basic, right? At the end of the day, I'm just repeating the terminologies here. But let us relook at convolution for a sample data set 0, 2, 1, 0, minus 1, minus 2. Probably I have reduced. Okay. So now instead of having a filter size of 1, let me take a filter size of 2, 5 and 1. Each one is a weight. So when I have a filter of size 2, I have 2 weights associated with the filter. Earlier I had only 1 weight, now I have 2 weights. weights of the filter. 5 and 1. There are 2 weights. So W1, W2 like that. So you can think of this as X1, X2, X3, X4 input data, W1, W2. So what does convolution operation actually do? It has to multiply and add, right? Integration, discrete domain, summation of product. So it has to do a multiplication and addition. So my feature map, when it is placed like this, 0 into 5 plus 0 into 1. 0 into 5 plus 0 plus 2 into 1, sorry. Okay, so 0 into 5 plus 2 into 1. So that will be 2. 0 into 5 plus 2 into 1. So you get 2. Then your stride length of your filter, stride can be 1 or 2 or 3. If you move the filter by one stride or stride of 1, this is a moving dot product or sliding dot product. So 5, 1. So 2 into 5, 10 plus 1 into 1, 1. So this will be 11. Is this clear? Then I move on to the next. With a stride of 1, I get same filter, same weights, 1 into 5, 5 plus 0 into 1, 0. So this will give me 5. Sorry? Okay, so the question is whether we have to flip it or not, right? For the purposes of this, we will assume that this is the flipped input. Okay. Actually, what has happened is, you will see that there are certain ways to do it. You can flip it, or you will also retain it this way. Okay. But for our discussion, let us assume this is the flipped g of g, basically. The convolve function after it's flipped is what we are considering. Let us assume like that. So let me proceed, because we are going to end up with a problem here. So I want you to see that 0 plus minus 1. So this is minus 1. I hope everybody is following what I am trying to do. Yeah. So this is not matrix multiplication. This is just a dot product. So this is not a matrix multiplication. We are doing a dot product between these elements. So 0 into 5 plus 2 into 1. So this is the operation that we are trying to do. So this is what we call as a sliding dot product. Okay, so that is the convolutional operation. So let us say we are already here. So this is 5 and 1. So minus 1 into 5 minus 5 plus minus 2 into 1 minus 2. So this becomes minus 7. What next? Unfortunately, the feature vector's length is already ending. So we can no longer have the filter dangling like this. You cannot have a filter dangling. So what we will end up getting is a feature map whose length is less than the feature vector's length. Okay, so the size of the feature map, which is output of the convolutional operation, reduces. If you have a filter size which is greater than 1, and it also depends upon the stride. Instead of using one stride, if I do multiple strides, the feature map length would have reduced even further. Okay, but we do not want this to happen, because we do not want to miss out on features. So what we will typically do is, whenever we have a filter like that is supposed to dangle over the input, we will assume this is equivalent to an input of 0. So this operation of adding zeros, usually we will add 0 on either side, because we will start from left end to right end. This is called as padding. So padding is done to ensure that when you have a filter whose size is greater than 1 and stride is different than 1, padding is done to ensure that the feature map is having the same size as feature vector. So in this entire statement, I have thrown all the terminologies I introduced. Okay. So if you are able to follow me, then the 30 minutes of my talking is a success. So padding is that operation. You can actually add more and more zeros. Padding. Depending upon the filter size, depending upon your stride. So in these both examples, I have used stride of 1. You can actually go to stride of 2. And then you will see that it will jump. And your feature map will go down in size. So you typically don't want. Okay, do that. In some applications you will do that, in some applications you don't want. So for us, we are not interested in reducing the feature map length. So we will use typically stride 1 and we will try to add padding to ensure that our feature map has the same size. So this is minus 2 into 5 plus 0 into 1, so this is minus 10 as feature input or feature vector. Okay. So let me go back a few slides. So now that I have introduced some terminologies, what we are trying to do in a CNN is we are trying to, after we have calculated the loss function, we are trying to optimize the loss by adjusting the weights of the fully connected ANN plus the weights of the filters in the convolutional layer. Okay, so what we are doing is we are trying to fix these weights. So we start with an initial weight, we do one forward pass through the entire CNN architecture, we will get an output, predicted output, we compare it with ground truth, we use a loss function to estimate loss, and we try to optimize that loss by adjusting the weights dou j by dou w, and weights now include the weights of the filters as well. Not only weights of the ANN on the back end, but also the weights of the filters. Okay? Does that make sense? So while we have approached or we wanted to be having a convenient method of not bothering about feature extraction, see, all this from fault diagnosis perspective is we did not want to extract features, right? We went for convenience, in some sense. And the cost we are paying for that is increased number of weights to be trained. So what does that mean? That means since you are feeding in raw data and you expect the machine learning method to extract features and then optimize, like come up with a prediction, naturally your time required to train is going to increase. Okay, so whenever you are doing ANN, you are already feeding in the feature vector, you are only doing 1/2 of this entire exercise, the number of weights are fewer and therefore the training time is shorter. So the convenience for us has come at a cost in terms of computational time, in terms of training time. Okay? So that is the first thing you need to understand. Additionally, you will realize that as I proceed, it is not just such a small filter with only 2 weights. You may have 8 weights, 16 weights, 32 weights. Because your input data set is not such a small length vector, right? It will be a large vector. Several thousands of data points. So your filter size can be 32, 64 and it's still much smaller compared to your input data. So and more weights you have, the training time increases considerably. Okay, so now let us look at the idea. So the next idea I want you, okay, so we'll go into the basics. Okay. So what typically we will do in a practical structure is, I will use this slide, because we will have raw data set which is processed. So when I say raw data set, it is not actually the signal that you capture. You do some filtering, you do some normalization, scaling like that, and then you have this sample, this is my raw data set. So processed data set, processed input. Then I have a black box. The black box has convolutional layer. I am going to call that as CL for abbreviation. I am going to number it as 1. And typically you can have another convolutional layer where you feed the output of the first convolutional layer as the input to the second convolutional layer. And you can do so on and so forth. Okay? But what you will do is, you will keep the, if you do it this way, you are retaining the feature vector length consistently the same. Whatever is the feature vector length here, you will get the same feature vector length. Alternatively, you can also add another layer called as pooling layer. So what does pooling layer do? Pooling layer is doing another operation. So that operation is, if the output from the convolutional layer is a feature map whose values are -10, 2, 5, let's say 6, 8, 4, -4, something like this. This is the, it doesn't really matter what size of filter I used, what stride, I'm not bothered. So this is the feature map of the coming out of my first convolutional layer. So how I got it, I'm not bothered right now. What is pooling operation doing? Pooling operation also uses a filter. Pooling layer will also use a filter. Okay? And for our applications, typically this filter size will be 2. And what it does is, it will try to identify the maximum value of the 2 samples that are covered by this filter. So in this example, we have the 2 samples to be -10 and 2. So the maximum of these 2 is 2. Right? So the maximum value is 2. So you call this type of pooling operation where you use a filter of size 2. It can be any size, to be honest, but greater than 1. Filter of size 2, and you use the maximum operation on the inputs covered by the filter. This is called as a max pooling algorithm or max pooling operation. Then what you will do is, since you have already taken these 2 and combined, you will move this by a stride of 2. Because the size is 2, you will move by size of 2. That means this starting point will move by 2 samples, and therefore your filter will now start here. For stride 2. So I want you to understand what is stride is equal to 2. Your input, your filter has moved by 2 samples. Again you will do the maximum operation. So between these 2, what is the maximum? 6 and 8, 8. So 8 will be your output. Then again stride 2. Max 4 and -4, 4. So what I want you to understand is, the pooling layer will have a filter, typically whose size is greater than 1, and usually 2 for us. what that will result in is it will reduce the length of the feature vector or feature map coming out of a convolution layer by half. So if you have 6, you will get 3. And this is possible because you have a filter size 2 in the pooling layer, and whenever you have filter size 2, you will have a stride 2 to make sure that, so you will cover the first 2, then you will go on to the next 2, and then you will go on to the subsequent 2. Okay, there will be no overlap. Okay. There is another type of pooling operation which is also quite popular, that is called as the average pooling. And average pooling means you take the average of these two and you give that as the output. Yeah, so feature map vector length will be reduced. So that is the purpose of pooling layer actually. Feature map length will be reduced. Okay, so this is very important. Otherwise, you are not, the whole purpose of introducing a pooling layer is to reduce. So from an image classification perspective, what the pooling layer does is, the feature extraction need not be done at a very minute level. So you don't have to go and extract features in pixel by pixel level, right? You can go wider, like zoom out a little bit and then extract features. So that is what pooling layer helps you do. So basically it kind of takes it like a bird's eye view or a top view or an overview, like just above, slightly zoomed out kind of a view, okay? And then extract feature from that setting. Now we have two options. So we'll go back to the architecture. You can either have a pooling layer right after a convolutional layer, or you can have another convolutional layer, and then you can have a global pooling layer, average pooling layer. Okay? But what is typically preferred in literature is you have convolution layer, pooling layer, convolution layer, pooling layer, like that. So this method is not very common. What is more common is you will have CL and PL. And that way the feature vector size would have diminished. The next CL would take a lower size vector, and the next PL will further reduce it. Next CL will take the further reduced order PL, like that. Okay? And this will go on until you have the right length for your feature vector for your fully connected ANN layer. See, if you have a raw data set, let us use some numbers, then you will appreciate it better. Let us take a sine wave, 50 hertz. Okay? So I am going to sample 100 points in that one cycle. So every 20 milliseconds there are 100 points. I am capturing for 10 seconds. So how many data points I have? In 20 milliseconds, I have 100 points. In 1 second, how many points? Sorry? Please do it and tell me. $5,000 only? So 500, 5,000. 5,000 points. So 10 seconds, I have 50,000 points. Right? Am I correct? So if I have 10 seconds of data being fed in, my feature like the input data will have 50,000 points. For my ANN, the input layer here is the features that we are to feed in. That is what this part has to do, right? What is the goal? Should we have 50,000 features? Should we have 10 features? Usually your input to ANN will be 20, 30, whatever that size we are looking at, right? So for our algorithm, in the example that we said, we used kurtosis, skewness, like that. There are 5 or 6 features only. So from this order of magnitude, this algorithm has to bring it to an order of magnitude which is much, much smaller. And that is why we introduce pooling layer after every convolutional layer to reduce. So you will see that it will taper. So the pooling layer will reduce the order by half. So if you want further reduction, you can increase the filter size of your pooling layer. Instead of having size 2, you can have size 3 and stride 3. Then you will go 1/3. Okay? So the intention is you have a huge data set as the input, but the dense layer does not need that many features, because then it will become too much of a training. You will just need maybe 30 features or 10 features or 50 features, right? So you have to design your convolutional layer and pooling layer such that the orders of the feature that you want to feed into the ANN is appropriate. If you poorly design it here, then this is going to consume a lot of time. So this is a problem that is known to us already. I'm just assuming it. So that is why I'm not bothering too much about it. So if I give you an ANN with 10,000 features, that is the input vector, then your hidden layer has to have so many neurons. Even if it has 2 neurons, you will see how many weights have to be trained. If it has 200 neurons, then probably you will go now, come back after a few days. Right? So it is going to take a lot of time. No. So this is just output here is the feature vector, feature map. This will be of the same size. This is being fed as it is. There is no reduction here. So from CL1 to CL2, the order is reduced. CL2 to CL3, the order is reduced. So by how much you need to reduce the order, it's up to you. And you can also decide that at different stages. You can reduce the order considerably here itself, or you can wait until 2nd or 3rd or 4th or 5th layer to do that. So they are hyperparameters. So now we have the term, right? So whether you use max pooling or average pooling is a hyperparameter. Yeah. So I have a slide on those things, on hyperparameter tuning with CNN, right? So what you can see is how many layers you have to add? Hyperparameter. What is the filter size in all these layers? Hyperparameter. The filter weight is what is being trained. The size is not. The stride is not. Okay, so there are so many things that you need to fix. So just for one convenience, which is to avoid extracting features in our case, we are making our life more and more complex. Okay. If you do this mathematically, see, these are all just convolutional operations and max operations or average operations, right? So you can actually write code to do the convolution max, convolution max, convolution max. And based on stride lengths, you can actually reduce the order. So then if you do the entire programming yourself, you can actually extract the features that is being fed into the ANN. But we will never do that. We will use a tool. Then we are black box. We have no clue what have been the features that the algorithm has sent to ANN, unfortunately. So which is a big drawback. Right? So
we can write the coding also in ML program as we are doing for instead of this pyramid. And so maybe that way also our requirements are going to be fulfilled, or maybe any other benefit we will get here, right?
So for our application, because of the nature of data set, the size, we can actually do ourselves the programming. It is a little bit more involved than using a tool, but you will have a lot more information about the system. As on date, I have not seen anyone go and develop that themselves. Most of the researchers have used the tools existing, and because there are so many hyperparameters to play with, you are going to get lots of variety of results just by using a tool, tuning different hyperparameters. And that itself gives us interesting information. And we are not bothered about what exactly are the features as on date. But maybe one research opportunity you all have is, if you write your own structure of CL, PL layers, you can extract these features and see how that impacts.
Actually, for our application, here for hybrid pyramid we are using for each and every sector. We are actually separated in many ways, and then so we are finding that suitable vector by our own program, like that we have.
That is wonderful. Yeah, you can do that. So what I'm trying to say is, the reason why exploiting this feature vector is useful is, let us say you develop multiple such, you develop your own program and you are able to tap into this point, right? Then you can feed in different data set and extract multiple feature vectors. Then you can create your own machine learning model like this, but not necessarily using convolutional operation. You can use an ANN. You can replace this completely with an ANN to extract features from the raw data set. Okay? So, yeah, this is probably going to be faster, but that is another way, if you know, if you have access to the feature set.
Like if you are adding coding in the programming, that may be having further divided into more samples, as you are saying, right?
Yeah, you will have more depth in understanding what is happening. But this is the basic idea. So you are going to add pooling layers to reduce the order of input data set into a small order of feature vector that has to be fed into your dense layer, which is the AN. Questions? Anybody is still with me, or everybody is confused? It's not yet. Yeah. So in the toolbox, all these black box things will happen, and what you will get is just the output. Yeah, exactly. Yeah, so you will tune different parameters, but ultimately you have to train this model, right? So this is just one data set. Like that, you have to collect several data sets, feed into the model, train it. So the weights have to be trained to optimize the loss. So this is an ANN. So you are still optimizing this loss function, dou j by dou w. But now the w includes the weights of each of these filters in the convolutional layers. Sorry? Mm-hmm.
The error is less compared to we get the approximately zero. So sometimes we get the weights of the data is negative. So then what
you may have to set it up separate differently then. So you will have to. I'm surprised how you got weights to be negative, but yeah.
That is overfitting, sir, actually.
Yeah. So usually, yeah. If you get such a system. Yeah. So we will see that in CNN you will have regularization requirement. Overfitting is quite common in CNN actually compared to even ANN. But you will have to use. Exactly. So that is why I am encouraging you. That is why I am encouraging you that this mathematical operation is not too difficult for our application. See, because of the nature of data set we have, we don't have to be bothered. We can probably try to develop our own layers. Okay. So,
data, our data, we are due to that we want to print out. So they get all the process okay. But want to change the
yeah, that is what we have to learn, right? At the end of the day, we have to do trial with hyperparameters, and you see how what is the best bet. Anyway, so going back to this, so we have learned pooling. Now I am going to introduce a more practical or realistic CNN architecture. So whatever I have introduced until now is not how typically you will see in reality. What will happen is in CNN, the good thing is, let us say we have my feature vector, so raw data set. So this is feature vector which is being fed into my CNN black box. I can have in the first convolutional layer itself, I can have filter number 1 of size 2. That means there are 2 weights with 1 filter. But in the same, so at the first level itself, I can have another filter of size 2 with different weights. So let us say this is W1, W2, this is W3, W4. So what that means is, I will get 2 feature maps from the first convolutional layer. So for filters W1, W2, let us say I will give some numerical examples so it is easier. 5, 2, 1, 3, 2, 5, 6, 7, these are samples. And then I am having 1, 1, or maybe I will say 1, 2. This is 0, 2 or 0, 1. Okay. So I am using 2 filters at the first level itself. Each of the filter is having different weights. The size and stride are same, but the weights are different. So what will I get? I will get feature map 1, and that is based on filter 1 weights. 5 into 1 5 plus 2 into 2 4, so that is 9. Then if I have stride of 1, this filter will move here 1 2 2 into 1 2 plus 1 into 2 2. So 2 plus 2 4. So this is 9, this is 4, like that. So this is first feature map. But I will also get another feature map 2, based on my second filter. And that will be 5 into 0 0 plus 2 into 1 2. So this will be 2. So what we are in practice, what we will see is, for every feature vector at a layer, so if you take in any layer the input as a feature vector, you don't have to have just one filter to be operated on the feature vector. You will have multiple filters of each different weights and even different sizes, and you can extract multiple feature maps coming from that one operation. So this is kind of parallel processing. So simultaneously multiple feature maps will be extracted. Okay. So now let us re-look at the architecture. We have our input. We have our black box starting here. In the black box I have a convolutional layer, but my convolutional layer introduces 2 filters. So that means I will end up getting 2 feature maps. Then I will add 2 pooling layers, one for each of the feature maps, to reduce them, and then I will use these 2. Again I will introduce 2 filters. So now my feature maps, this one will become 2, this one will become another 2. Then I will have to have 4 pooling layers, like pooling layers for each of the feature map. Is this clear? Like the dimension? So this is how a practical CNN will look like. So what is now happening is, we are reducing the length of the feature vector, but we are increasing the dimensionality or the depth of the number of feature maps have increased. So we are stacking layers of feature maps, but the actual length itself will reduce because of the pooling layer. Because if I had 100 points here, this will, if it's a 2 pool, max pooling of filter size 2 with stride 2, I will get only 50 points. Right? And then here, if I do it, I will get only 25 points. So the length of the feature vector is decreasing, but because of multiple filters being used, the depth, the stacking of feature maps are increasing. So what we will essentially have is, we will have stacked multiple feature maps. But our ANN requires a single dimensional vector. Right? So our ANN input is a one-dimensional vector. So all the stacks have to be flattened out. And that is why we will add a flattening layer. So we will just probably take this and put them like this into a one-dimensional vector using flattening layer. And then we will feed it into our dense layer, which is our fully connected ANN. Is this clear? Any questions? So the purpose of flattening layer it flattens or basically converts the stacking of multiple feature maps into a single one-dimensional vector for our dense layer to use. Flattens the stacked feature maps or multiple feature maps. Into one vector for the ANN to use. This ANN is usually a fully connected ANN. So now let us look at the number of weights that need to be trained. So first convolutional layer, we have, let us say, 2 filters, each of size 2, then we have 4 weights. That generates, so here we have 4 weights. Right? In this 4 weights, again 4 weights, right? So it increases. So as you add more and more layers with even just 2 filters, the number of weights grows exponentially, like considerably. And all these weights have to be optimized to minimize when the loss function is to be optimized. So is it clear? So that one convenience that we are looking for has resulted in increasing the dimensionality of like the order of complexity that we are requesting the algorithm to solve is many folds. Okay. So what you will realize is, in CNN there is ANN part which has its own hyperparameters, like number of hidden layers, layer size, okay, initial weights for the neurons, initial bias values, regularization strength, and then optimization algorithm, learning rate. These are the hyperparameters associated with ANN itself. And then when we add convolution pooling layers, multiple of them with different filter sizes and flattening layer, so where hyperparameters increases considerably. And because the algorithm depends on hyperparameters considerably, the CNN performance is affected considerably if you choose wrong hyperparameters or inappropriate, I would say not optimal hyperparameters. There is no wrong hyperparameters, there is like something that is not optimal. So the whole problem of coming up with a machine learning model now boils down to setting many values. And we have no direct mathematical relationship to say that if I set these values, this is what I will get. So it is like shooting in the dark. So how do we actually tune hyperparameters is a big problem in itself. So if you are not interested in condition monitoring, if you are not interested in electrical power, if you are interested only in machine learning, this is the nature of problem you can work on. Right? How to optimize hyperparameters for different applications. And all this we are talking with one dimension. The original purpose of CNN is image classification, so 2D, 3D like that. So everything gets, like the magnitude becomes quite high very soon. So the hyperparameters tuning, some of the reported approaches are grid search. Grid search means if you have 20 hyperparameters, you fix 19 of them. You vary one of the hyperparameter. Say for example, the number of hidden layers in the ANN is the hyperparameter you are planning to vary. Usually it will be 1, 2, 3 like that, right? So you will just set all the 19 other parameters will be fixed, same value. This number of layers alone will be changed to 1, 2, 3. Rerun. So you will train the model for minimum loss. Then when you work with validations data set, you will tune the hyperparameter and see how the tuning of hyperparameter impacts the validation set's loss. So the loss associated with validation data set. So for all hyperparameter tuning, we are taking the loss of the validation set. So when you tune the hyperparameter, you will check whether this has resulted in increase in the loss of validation set or same or reduced. If you reduce it, then it's a good parameter. If you increase it, that's worse. So this is for one. You have 3 values. Then you go for next hyperparameter. Let us say optimization algorithm. You change different algorithms. You see what is the impact. Then you say number of neurons in the layer or number of convolutional layers. What is the filter size? So like that you can do one at a time. And that type of tuning is called as grid search. And as you can quickly realize, for a network which is reasonably sized, which is not even big, which is reasonably sized, this in itself will be a big project. You will be tuning. And you may not be able to conclude at the end of the day, like what exactly gives you the optimal results. Okay? So the second search that is recommended is, instead of doing grid search of every hyperparameter tuning, keeping others fixed, we will do random search. We will set randomly. We will see. Then we will again change randomly. We will see. Compare the two. Whichever is better, we will take that, discard the older one. Again, do random search. But when we are doing random search, we have to be careful. Even in grid search, we have to be careful. See, there are certain hyperparameters like learning rate. They will be of the order of 0.001 or 0.1. There is regularization weight, right? Regularization strength. If you remember, alpha times L2 or L1 regularization, right? Regularization strength. They will be typically 0.001. So this is 0.01 like that. So how can you discretize when you are doing random search or grid search? Initially you set to 0.01. What should be the next value? Should it go to 0.011? Or should you go to 0.015? Or should you go to 0.02? Or should you go into 0.1? How do you discretize? Right? So in random search, typically generally we recommend, if you are doing random search, we go for a log scale variation. Rather than just going for 0.015, 0.02 like that, go for a log scale variation. So you can broaden your search area quicker. That's the idea. Okay. So these two are there, but because of the complexity of the networks, the layers and the model itself, modern research has been focusing on a machine learning algorithm to optimize these parameters. Ultimately, these are parameters to be optimized. So for example, can you try naive Bayes algorithm? How does that impact? Like that. So some machine learning optimization algorithms are being used to optimize these hyperparameters. That is another research that is happening right now. Okay? Good. So I think I have given a reasonably brief overview of one-dimensional CNN exclusively for the purpose of fault diagnosis, where our goal was to avoid the inconvenience of us extracting features and feeding into an ANN. Rather, can we use a model which can automatically extract features and feed it into an ANN? Okay? So this is the purpose of this presentation. In this process, I have introduced you to some key terminologies which are consistent with whether you go for 2D CNN or 3D CNN, the same terminologies will be used. Filters might be called kernels, but otherwise things will be same. Stride is stride, feature map, feature vector, padding, they are all the same terminologies. Okay? Questions? Any? So for those of you that came a little bit late, I just wanted to inform you that unlike our usual schedule, today because of the valedictory function, we will be having a break, like there will be just a recess break, and then we will be reconvening, we will do some activities and then function, and then only we will have some tea and snacks. Okay, just for your information. So what I will do is I will give a 10 minutes break at this point. When we reconvene, I have shared a research article which is the same article I shared 2 days ago, but at that time we focused only on the ANN part. Now I want you to look at the CNN part and see what parameters have been used, how are the results with ANN, like that, and you will see that, I mean, you will identify once you go through it what other things can be done. Okay? So that is the activity we are going to do starting at 11. So we will meet at 11. Thank you. Is a simple activity. So I have shared an article with you in the group. So please go through the section that talks about CNN. I just want you to read through it without any, I mean, it's very simple. It's a simple section. You should not take you long. Go through it. Then what I want you to see is try to identify things that we just discussed, like what are the layers, what is the architecture, what are the layers, what is the filter, how many filters have been used in each layer, what type of pooling layer has been used. All those basic questions you try to identify. Okay? So that is the main purpose of this activity. That's the first part of the activity. Try to understand what is there. And then you can ask questions like, why did you have to do it this way? Can we do it another way? Like that. Okay? So this is a basic activity. So I'll give you maybe 3-4 minutes, not longer than that. It's just one paragraph or maybe a couple of paragraphs, so it should not take you long. After that, we will look at the results between ANN and CNN, and then we will see what that is meaning, like what is the implication of that. Okay? Anyway, so that is the first step. So we will read through the CNN part, try to identify what parameters have been used, and then we will spend some time discussing, and then we will go on to the results part.
ఉండాలి ఇది కూడా అక్కడ మన డిపార్ట్మెంట్ లేదా మన డిపార్ట్మెంట్లో మనం తీసి పెడతాం కదా ఒకవేళ అక్కడ లేకపోతే సార్ సార్ అట్లా ఉంటే అయితే ఉన్నాయి ఉంది కాబట్టి తెచ్చుకున్నాను వచ్చినప్పుడు అయితే ఉంది సపరేట్ ఉంటుంది
So it's gone through the first section. We need some more time, one more minute maybe. One more minute.
So what did you observe for this in this article? What caught your attention? Did you identify the architecture? Look for the architecture. What do you think about it? What do you think about the architecture? Well, that's fine. But what do you look at when you look at the architecture of the CNN?
Global average cooling.
So what is your opinion now? So with this model, what do you think is the advantage? What do you think would be the drawback? Computation time is more. Why? So the first thing is we have not gone on reducing the input data, right? The feature map length has not been reduced every time. So it's only reduced once. Yeah. So the feature vector that is being fed into the fully connected dense layer might be higher, depends on the input. So that is so it's not a traditional architecture. What you would typically expect. Why do you think this could have been used, or when would you prefer to do it this way? Less number of data. So basically, if your input data set is not in millions, if you are something that you feel like this is not too many, you do not want to reduce it further. You want to preserve the features. Right? So then you do not want to throw out the features using multiple pooling layers.
Another point is we have limited, actually we expected limited features from this one time system. That is number of feature extraction, that is extracted feature will be less in numbers.
Yeah, but that we have not done it that way. That's what I'm trying to say. So this architecture, the feature extraction coming out of it, it's not reducing the number of features. It's trying to preserve as many features as possible.
It's a standard
dimension reduction has not happened. Exactly. So your ANN is going to take longer time as well because there are lots of inputs to it. So this architecture may be good for our application, but not a good architecture in general because if your input size is very big, then you're not ready. So
Here the input use is less, maybe they have it. If I take the same application, I use a large number of inputs, the data, it's seconds, more seconds, then I have to go for.
yeah, probably. So what I'm trying to say is, whenever we read through such articles, from now onwards, what I encourage you to do is think whether this is what you will also do, because you may not get exact application related to your like exact articles related to exactly your application. So try to see whether you will adapt it to your requirements, what changes you can try, what hyperparameter variations you may do, etc. Okay. So that's the fundamental objective. So when you learn about another work, that's the first thing you need to explore. Okay. Then the filter size. Did you notice that? How many filters? How many size 2? So how many filters are in first convolutional layer? What is the size of each filter? 60. 8 filters are there. So what does that mean? 8 feature maps will be created out of the first convolutional layer. Second convolutional layer will create 8 for each of the 8 feature maps. So in the first, so you are creating a stack, depth, right? You remember, that's what we discussed. So when you give the raw data, so we are looking at this diagram here, 16,8, 32,8, 64,8. So the 8 is the number of filters per layer, and 16 is the size of the filter in this layer. 8 filters means you have feature vector, which is the input layer. You are using 8 different filters and simultaneously creating 8 feature maps. Yeah, so the 8 weights. No, that is the size. It is the number of filters. So if you only have
one filter,
number of filters. Number of filters is 8. Each filter has 16 weights. Okay, do you understand? So the first convolution layer produces 8 feature maps. When that goes into the second convolution layer, each of the 8 feature maps is further producing 8 more feature maps. So we have 64 feature maps. Each of those 64 feature maps will result in 8 feature maps. So that many depth, so you can imagine a stack of feature maps, and that is the stack that we have 64 into 8. And then we have to do a global average pooling and a flattening layer, and then we will have a fully connected layer. Okay. So the flattening layer is probably not explicitly shown, but you have to do it because you have created a stack of feature maps. Is that clear what I am trying to say? And regarding the size, in the first we have 16 weights for each of the 8 filters. So 16 cross 8 is the number of weights in the first level. I hope I'm making sense. But I do not know if you are following me. So let us go back. So this is the diagram I want you to keep in mind. So I told you that you can have simultaneous filters for each layer. This 2 is the size. Number of filters is 2 in this case. In that article they have mentioned filter size of 16. That means 16 weights. And number of filters are 8. So in the first layer itself we have 8 filters with each filter having 16 weights. So 16 cross 8 weights have to be optimized in the first layer alone. Okay, is that clear? So you try to understand this diagram or keep that diagram in mind. all we are creating is we are creating simultaneous feature maps. So imagine each one of you is going to act like a filter, and I am the signal. So each one will give an output feature map. Right? So when you interact with me, you are going to get something out of it. That is the idea. So parallel, we are doing it one at a time, and then feature maps, so many feature maps will be created. So the second one has 32 filters.
8. That many weights have to be optimized by the algorithm. Just on the CNN side. Then you have fully connected ANN, which might have its own hidden layers, its own neurons, its own weights. Okay. The classification layer is nothing but the output layer of ANN, which would typically have a softmax function or some kind of non-linear activation. Okay. So hyperparameters, learning rate, learning dropout factor, I don't even know what this epsilon means, maximum epochs, regularization. So one thing I wanted to talk about regularization, typically in CNN we will not use L2 regularization, although in this work we have used L2. The most common regularization in CNN is L1. We typically want many of the weights to disappear. So what is the difference between L1 regularization and L2? L1 is sum of all the weights, absolute sum of all the weights, right? Whereas L2 is weight square sum. Like this will be, I think, absolute. You want to make, so you will add this to the loss function or the cost function, basically to minimize the loss function. I wrote a wrong expression there. It should not be dou j, it has to be loss function plus, so the loss function plus regularization function with a weight, with a strength. So loss function plus the regularization function times a strength. So here we have used lambda, so let me use lambda. So in CNN typically we prefer L1 regularization because we want the weights to disappear. We want some of them to not appear in the model training. We want to create sparsity. Whereas in ANN we do not want to create sparsity. We want to keep it, we want to keep the weights like the neurons to be present in the model. Okay? So that is the difference. So in CNN we want the neurons to disappear. In ANN we want to retain them. So the most common regularization we will see is L1 for CNN and L2 for ANN, typically. In this work we have used L2. Okay. But these are just trial and error, as you would have read in the article. We had to do some basic trial, what should be the filter stride, size, all those things. Like the stride is 2, I think has been optimized or found to be giving optimal results. All those things have been identified. Okay. Anyway, so we will go on to the results section now. I will give you another 5 minutes max. What I want you to do is compare and come up with some opinion about what you think might have happened, okay, based on the results that you are seeing for CNN versus ANN. Okay. Unfortunately, this probably did not compare the computational time in the article. If that were given, it would have been very easy for us to say.
So let us discuss. So first thing, you would have seen the results section. What is your opinion about the results? CNN the presented work says claims that CNN has 100% accuracy. Okay? So if you see such a thing, what should be your next question? What I'm trying to say is, so what should you suspect when you see a 100% prediction accurate? Do you think this model would have been overfitted?
No, that is overcome by some other approach. In this it is mentioned that they have used the unused data set.
Nevertheless, we still do not know, right? What I'm trying to say is, when you have such a high accuracy, the first thing you need to suspect is whether the model has gone into overfitting, right? So, if you were to present your work, or if this was submitted to you, what question would you ask? Say, I'm submitting this article to you, I'm the author, let's say, and then you are reviewing it and you saw this result. What question will you ask me? What additional information would you expect from me? That's all I'm asking. Sorry? Yeah, but what is the technical information that you will say is you would want to look at to see whether this model might have been gone overfitted or it's okay? How would you check? See, ultimately it's an ANN there, right? So can you look at the plot of loss function with epochs for training data set and validation data set? And if you recollect, there was a plot that I showed you, right? Yes, loss function versus epochs. I said that this would be the typical nature of a training data set. For training set, the loss would have gone down. But if the model were so overfitted that this is true, but the validation set would have resulted in increase in loss. Right? You will see beyond certain point. This is where we are looking at probably, but this plot, if we was presented, right, it would have been helpful. Some additional information we need to check. What other methods you can check? Like in this paper, there was something mentioned about overfitting, right? They had. Yeah, true. The test data was unseen, but. But regularization, has anything been mentioned about regularization? So that is another thing you can check when you have suspicion. You can see how things have been regularized to mitigate overfitting effect. L1. So whenever you are looking at articles, there are a few things that I want you to look as a next step based on this workshop. When you look at an architecture, see why this architecture. When you look at the filter size, number of filters, visualize it to see how impactful that is, how many weights that are being trained. Then you can compare with an ANN in terms of computational time. Unfortunately, computational time is not, is there, how much is there? So you can see the order of magnitude, right? So 7.8 seconds versus 256 seconds for the same hardware. So that's the complexity. So what is the convenience we went after? Feature not provided by us. What is the computational cost we are paying? Extremely higher, and this is for a very small data set. Okay. So that's the problem. Usually magnitudes will be millions. So then you can see computationally how intense training will be. So these are the aspects I want you to look at when you are looking at through any data-based article in future. So try to be critical, or try to ask questions. So that is my major comment for the last comment for the session. You don't have to take everything as the information is presented, but ask questions and be critical about it. Anyway, so it's 11:30. So we will move on to the next part. So I told you yesterday that I will be collecting some kind of feedback, at least to some of you I told. So this is the time. So what I want you to do is take a piece of paper without discussing with anyone beside you or in front of you. You are going to write feedback on 3 points. You have about 6 to 7 minutes to do that. Okay. So the first one is 3 things that the instructor must change to improve this course. So what should the instructor, which is I, must change to make this course more beneficial to you? See, I do not know what your expectations are. So from your expectation perspective, no matter what it is, you can say this. And then 2 things that the instructor must continue doing so that the course will be beneficial to anyone that takes. And the last thing is 1 thing that you learned out of this workshop, 5 days. Okay. It could be just a name of a person, or it could be something technical that is different, but I am expecting the technical aspects. Okay. So these are the 3 questions. So after you are done, we are going to do a review of all the 5 days sessions for 10-15 minutes, and then I will open the floor for questions. So you have time until 11:40. And by the way, I will be collecting these sheets. You do not have to write any name, so keep it like anonymous. So if you are done, you can just leave the feedback sheets on this table up front. Maybe one of you can collect and just bring them here. That will be easier. I'll give you one more minute and then we'll go into the review of the sessions that have happened. Okay, so we will proceed. If you want, you can always submit it later too. That's not a big deal. Okay. So we'll go into quick review of what has been done so far. I think there is no feedback forms coming your way. So that one was for me. This one is for the government. Okay, so let us quickly review. On day one, I talked about why even this topic is significant, non-invasive fault diagnosis of propulsion motors in EVs. I think I convinced you all that EVs is going to grow considerably in the next decade, and all of them will have a motor for sure. And depending on the class of EVs, whether it's a light electric vehicle or medium or heavy duty or off-road, whether it's an electric ship or an aircraft, then propulsion motor that is being deployed is very different. So you have pretty much every kind of motor in EV industry. Okay. So the good thing is you can choose any motor that is available to you, and that is in some sense a propulsion motor. Whether you choose an induction motor or a synchronous motor with DC excitation, synchronous motor with permanent magnet, a brushless DC motor or an interior permanent magnet machine. Okay. All these motors are being used in propulsion sector or EV sector. Therefore, there is a lot of, like the motor itself is, we can consider them as motor agnostic. The diagnosis is, we are not really focused on a specific motor, we have treated the motor agnostic diagnosis. The first and most important thing I told is the percentage of faults that happen in motors. So we said bearing faults are the most dominant with about 40% failure rate, and then stator turns fault or winding faults is about 36%, and then the rotor and eccentricity faults are less frequent. But please note that these data are based on industrial motors, right? And for as in one of the sessions you were presented with information that when we have switched inverter driven motors, the stator turn failure might increase because of partial discharge and stress, voltage stress that is being encountered, right? So this figure might change when we have more data with EVs in the next decade. Nevertheless, amongst all, in this workshop, the focus was on air gap eccentricity fault, even though it was only 10 to 15%. The main reason why we focused on this is because, unlike traditional industrial motors, EV motors have much smaller air gap. So the air gap length has greatly reduced in EV motors. In fact, I presented you with some information from literature that 100 kilowatt motor has an air gap mm of 2 mm, air gap length of 2 mm. Yeah, because most of the EV motors are permanent magnet type, and we want them to be power dense. We want to put them in a compact space. We are really designing it that way that the air gap length is really tiny. And that is why air gap eccentricity was focused upon. And also bearing faults will indirectly be resulting in eccentric faults. Okay. So in eccentric faults, we have classified as static, dynamic, and I said that mixed eccentric is the most common type. But invasive fault diagnosis is also ruled out because of the same reason that the air gap length is very small. So non-invasive technique is the only way or only option. Amongst that, the traditional approach was current signature analysis, and the drawback of current signature analysis is it will not work well for changing operating conditions. So if you have a steady state operating condition over long periods of time, you can acquire current, you can do signal processing and check. But in EVs, ensuring that the motor is running at one speed with same load for extended period of time is very difficult. Because of this change, just applying basic current signature analysis is not effective, or it's going to be tricky. And also there are other aspects that can kick in. One of the things is, no matter how well motor is assembled, with age there might be some degree of eccentricity that might creep in, resulting in current signature getting corrupted. So I showed you the experimental result versus simulated result. The experimental result had much more noise or much more fault frequencies, even under healthy condition. Okay. So the current signature analysis is, though powerful, currently used in industries, might not be the best one for EV sector. So we explored machine learning methods. And the first one we explored was KNN, which is not which cannot be considered as a machine learning approach simply because there is no model that is being developed. Right? So we are only trying to find the nearest neighbor and vote based on the nearest neighbor's label. There is no concept of once I train, there is no model that I can use quickly to verify. See, in case of ANN and CNN, the advantage is once you train, even though we spend 300 seconds to train a CNN model, once that model is trained and available, the test point, if you give it, it's just going to spit out an output quickly because the model exists. But with KNN, there is no such thing. Okay. So KNN will fail if you have more and more data points. Because it's not fail, it will take more time. It's time intensive. Okay. So this was one of the algorithms. Principal component analysis, I introduced that to you. So it's basically to say that we assume all the given data points are lying along a principal component. With that assumption, we check the error. If the error is high, we assume that the errors are along another principal component. With that assumption, we check. So, depending upon the feature vector's dimension, we will have that many number of principal components. And typically, if the features are not correlated from one another, they will be along the principal component. They will form the principal components themselves. But if the features are correlated, then you will see some of them will not have significant useful addition to make. So if I plot principal components, and the principal components themselves can be solved as eigenvectors of the covariance matrix formed from the feature vector or the input vector. Right? So we can solve for principal components using linear algebra. So you solve for eigenvectors. So eigenvectors is, you can solve them by solving for eigenvalues of the covariance matrix that you can form for the given data set. So if the feature kurtosis and RMS is given, there's a two-dimensional feature vector. So you will have a covariance matrix of 2 cross 2. Then you will have eigenvalues from the covariance matrix. Once you have solved for eigenvalues, you order them based on magnitude in descending order. So the eigenvalue of highest order will be placed first, the next eigenvalue of next magnitude will be placed next, and so on and so forth. So the one that has highest eigenvalue is the principal, the first component, and then so on and so forth. So typically you want, so you will see that this is how the eigenvalues and order, number of principal components, right? So the number of principal components versus eigenvalue plot. As you go along, if you see a diminishing eigenvalue, you can actually reduce the order of the feature vector by ignoring the low magnitude eigenvalues. If you see this trend, if you do not see this trend, then you cannot reduce the order. That means the vectors are already uncorrelated. Okay. So these are some things that I presented. Of course, you made a brave attempt in the lab to implement KNN, and you were so advanced that you implemented with raw data just like how you do in CNN. So you are trying to go to day 5 already. Anyway, so after that, I introduce you to the terminologies associated with artificial neural network, and one of the things that we saw was in artificial neural network, there is an input layer which is typically again feature vector. So features have to be extracted and have to be fed in. So let's say RMS, kurtosis, like that. So there is input layer, and we will look at a fully connected neural network. That means a fully connected network means a neuron will be connected with every entity from its previous layer, and each one will have a weight, and there will be x1, x2, x3. So the mathematical operation will be w1 x1 plus w2 x2 plus w3 x3 plus a bias term. And then this entire thing will be going through a nonlinear activation function. So function of, and that nonlinear activation function can be a sigmoid function or a tan hyperbolic function or a rectified linear unit function, like that. So there are several, and then the output will help in classifying. Okay, so these two will result in some classification. So these are the output layers. So the output layers are also neurons. So this is a hidden layer. This is the input layer. This is the output layer. And from the output layer we will have predictions. Okay. If the hidden layer number is more than 1, we call that as a deep network. Otherwise it's a simple ANN. And the output predictions will be compared with ground truth. If there is any error, you will try to minimize the error or optimize the error by changing the weights in the network. Okay. So this is what we learned in ANN. One of the things we learned is how to do weight calculations or how to change weights. So back propagation was introduced. So back propagation is typically done by identifying the local gradients. Let's say there is an error function which is a loss function, y minus y1, y1 minus y1 hat, absolute value of this. If this is the loss function, you take the derivative of it with respect to y1 itself. That will be the local gradient. So dou j over dou y1 over dou w. What is dou y1 over dou w? So if you look one layer below before, there will be a weight here. So this y1 would be wx something. So you will apply chain rule for this. Dou y1 over dou w is equal to dou y1 over dou x into dou x over dou w. Like that. So you will do backward propagation to find the local gradients, and you will use it to find the overall gradient of the system. Okay. So this is what we learned, and we know that we have to train this model, and then we have to validate it, and to minimize the chances of this model getting overfitted, we will have to regularize it using a regularization equation that will be added to the loss function or the cost function of the optimization problem. And today I introduced you to CNN, which is a layer up preceding the ANN model, and here the convolutional layers plus pooling layers plus flattening layer is added. The whole goal was to take just a one-dimensional raw data and let this generate features for the ANN, and then the rest of the process is still followed, except that now more weights have to be optimized. Okay. I hope you all recollect what we have done. And when we did all these things, yesterday we also discussed about the opportunities and challenges in this field. So the major challenge was identified with respect to data collection. So we said research is now going towards digital twin to generate data, okay, and machine learning model based digital twin to generate data. And then with respect to feature selection, there was another drawback we discussed, and today we discussed about CNN, which kind of addresses this problem. But there are more algorithms that can do this. Okay. So in a nutshell, this workshop has introduced you to some foundational aspects of condition monitoring using non-invasive techniques, primarily machine learning models, with the goal that you will continue working in this field, or at least continue learning about them. And that is all I have to say. In 5 minutes we have the validatory function. Right? So maybe I will stop here. If you have any questions, I am happy to answer. Thank you. By the way, I will be sharing the slides, annotated slides via the group, and you have an exam this afternoon. I think it's going to be online. It's going to be via Google Form or something like that. So it will be slightly easier for you to do from wherever you are.